Welcome, ladies and gentlemen, to a continuing study of Ohm's Law. You see on the screen where we left off last time, kind of a summary page of some of the things that we covered. And we're going to continue today by expanding on Ohm's Law and its usage and in understanding the particular concepts involved, as well as a few random facts and concepts that relate to circuits in general. Let's go. All right, the first thing I want to cover is the term voltage. Okay, it can be confusing. We're going to try to expand on that definition a little bit today, but you do see several terms used interchangeably. Voltage drop, sometimes we say voltage drop, sometimes we say potential difference, and sometimes we even an old-fashioned word, EMF, which stands for electromotive force. These three terms, for our purposes anyway, can be considered synonymous. All right. The second thing I want to talk about is ohmic versus non-ohmic materials. Okay, and all that means is that some parts of a circuit, okay, some things that fit into circuits obey Ohm's law, and other ones don't. Okay, so for an example, it turns out that a light bulb, actually, generally speaking, is a non-ohmic material. Okay, and all that's going to mean is that on a graph, okay, if we graphed voltage versus current for a light bulb, it would look like this. It would not be a straight line. Okay, really that's all you need to know. You don't really need to know more than that. We can assume every material in a circuit to be an ohmic material. Okay, for example, a resistor is an ohmic material. It obeys Ohm's law. All right, the third thing I'd like to talk about is AC versus DC. Okay, it's a common term, right? Got the rock band named AC/DC. And that's just talking about the way that current flows in a circuit. Okay, when you have a battery driving a circuit, okay, like we did in the simulation, you could see in the simulation that the electrons moved steadily, right, from the negative end of the battery to the positive end, right, in one flow. Okay, that's called direct current, right? Any circuit with a battery in it is going to have direct current. You think of the battery as a pump, and it's only pumping in one direction. Well, it turns out that most of the electricity that runs our society is actually a different kind of electricity. It's alternating current, okay? And just as the name implies, what that means is that the electrons go a little bit this way, and then they go a little bit that way, a little bit this way, and a little bit that way. And it turns out that they do that, they switch directions 120 times a second, okay? 60 hertz, that's called, 60 hertz. Okay, and you see that on some appliances, all right? So any electricity coming out of the wall, anytime you plug into a wall outlet, you are now accessing AC current, okay, or AC, I should say, alternating current, okay? That's why a lot of devices have those little boxes, right? Your cell phone chargers, they have those little converters, okay, and what they're doing is they're converting AC, alternating current, to DC, direct current, so that they can charge your battery. So, two different kinds of current. And then finally, there's a special type of material called a superconductor, okay? And the defining feature of a superconductor is really quite remarkable. A superconductor has zero resistance, okay? If you could come up with a superconductor that worked at room temperature, you'd be probably the world's richest person, okay? Right now, we do have superconductors, but they're made from very exotic, okay, as in expensive materials. And even those exotic materials only become superconductors when you make them super cold, as in approximately negative 200 degrees Fahrenheit, maybe a little warmer than that. Okay, you've got to bathe them in liquid nitrogen to even have them be superconductors. So it's not feasible today, but it's certainly something to look forward to in the future. All right, we'll go to the next page, and we're going to do two simple calculations here with the two formulas that we had last time, okay, Ohm's law, as well as the basic definition for current, okay? So you see on the screen two problems written out. I'm going to work those out in a minute, but I do want to also reference the table that I've come up with here. A lot of students have trouble, keeping straight what a quantity is versus what the unit is that we measure it in, okay? So for example, voltage is measured in, the symbol for it is the V, but it's measured in volts, right? So you want to keep straight the quantity versus the unit used to measure the quantity, right? The quantity is time, but we measure it in seconds, okay? So I've provided that there as an additional clarification. Let's take a look at this first problem. Okay, what is the current flowing in a circuit with a 6-volt battery and 4 ohms of resistance? All right, so I can use this drawing here of this circuit diagram, right? So I got a 6-volt battery, okay, and there's 4 ohms of resistance right here in this resistor, okay. This, by the way, this symbol, okay, this funky looking symbol is the Greek letter omega, as in the alpha and omega, okay, it's a capital omega. I would expect you to learn how to draw it. All right. We are going to use Ohm's law to solve this problem. Very simple. Okay. Here's Ohm's law. The 6 goes here. The I is the unknown. Right. The 4 goes there. I'm going to divide both sides by 4. Okay. And that's going to come out to 1.5 for the current. Okay. 1.5. And the units, as you can see from our table, the units for current is amps. All right, so that's a very simple problem, and it's because the formula is pretty straightforward. Okay, you've worked with a lot of 3-letter formulas this year. I'd expect you to do this kind of problem pretty easily. Okay, let's go down to the next example, which is an example of using the current formula, okay, the formula for current, and I'm going to write that again here, okay, but let's take a look at the problem. How many charges flow past a point in this wire in 2 minutes? Okay, so imagine you're an observer somewhere in the circuit, say right here, okay, like you're a little microscopic Mr. or Mrs. Physics, and you're shrunk yourself down to observe the activity at the atomic level. And what you know, there's current flowing in this wire, okay, we've now determined that it's 1.5 amps, okay, and what we want to know is if we're sitting here, okay, for 2 minutes, how many electrons are we going to see flowing past us, okay? So let me show you how you might use this formula to do that. Well, the 1.5 is going to go here for the I, okay? And it turns out that the Q, the amount of charge, right, the number of electrons, that's unknown, okay? But the time is known, it's 2 minutes. However, remember that we always have to put our time in seconds, okay? So I'm going to put 120 seconds, that's 2 minutes. And then I just multiply both sides by 120, right? Multiply both sides by 120 and I get Q by itself. Q is 120 divided by 1.5, that's 180. And the units for charge, okay, it's not in the table here, but if you remember from last year in electrostatics, it's coulombs. Okay, and that's a lot of charge, right? That's 180 dump trucks passing by you in a minute, in 2 minutes, okay, or 90 every minute. Now, we didn't ask for the number of coulombs, we asked for the number of electrons. So then we have to do something that we did last unit. Okay, I wrote it out in kind of dimensional analysis form. Okay, we know that every electron has this many coulombs, right? Some minute amount of coulomb. So we're going to divide that incredibly small number into 180, and we're going to get this really, really large number, which remember the coulomb is a super large unit. Okay, 1.1 times 10 to the 21 electrons is what we're going to get up getting. So what that means is if I stood in the circuit there, right, microscopic me shrunk down, I stood there in the circuit for 2 minutes and observed 1.5 amps of current, what that means is that this number, this total number of electrons would pass by me, right, a huge number. Okay, let's get to the centerpiece of today, which is the coal mine analogy. So let me take the same circuit and go to the next page with a little more space. Okay, so again we have our 6-volt battery. All right. And we still have the same 4 ohms of resistance. Okay, let me clean this up a little bit here. And the 1.5 amps. So what we're going to do is we're going to use a coal mine analogy. Okay, in the coal mine analogy, the battery, okay, the battery is the mine. Okay, and coming out of the mine are coal cars, right? And the coal cars are full of coal. Okay, now in the case of a circuit, okay, the carriers of energy are the electrons, the charges, but we don't count in individual electrons, we count in batches of charges called a coulomb. So in our case, every cart is going to represent 1 coulomb of charge. And, okay, just like the coal represents energy, so in this case, the charges are carrying joules of energy, okay? For a 6-volt battery, every coulomb of charge is going to carry 6 joules of energy. In other words, 1 volt is actually equal to 1 joule per coulomb. Okay, and you noticed from using the coal mine analogy, okay, or excuse me, from using the simulation in the lab, that the charge, okay, doesn't get less and less or more and more as it goes around the circuit. It actually stays the same. So what's going to happen here is that once it rounds this corner, nothing's changed, right? Now I'm going to add one more thing to this, okay? Because I have 1.5 amps, I'm going to multiply this by 1.5. Multiply this by 1.5, okay? And I can draw the same cart here again because I have yet to come across something in the circuit that uses up energy, right? So I still have all 6 joules. We're going to neglect a little bit of resistance that the wires have, right? Now ideally, in reality, okay, the wires are using a little bit of coal, so to speak, right? The wires are absorbing a little bit of energy. It's kind of like the equivalent of like a couple of lumps of coal bouncing off the coal cart along the way. But for the most part, all the coal's in there until you get to the load, right, in the circuit, which is like the power plant. Okay, so in our coal mine analogy, the load, which could be the motor, the light bulb, the heater, right, whatever it is that's using energy, that's where the coal goes, okay? I forgot the 1.5 here. I got to have my 1.5 multipliers just show the 1.5 amps of current, okay? So now notice what happens. Notice how this coal cart is different when it comes out, okay? The coal cart's still there, right, because the power plant does not consume the coal cart, but it consumes the coal in the coal cart. In the same way, a circuit does not consume the charges, only the energy that the charges carry. So coming out of the load, you now have still the same number of coal cars, but now the coal cars are empty. And then finally going back into the battery, okay, same thing, 1.5 coal cars every second, but they're empty now, okay? This analogy will force your brain to tell the difference between voltage and current, okay, and how voltage, which is a kind of an energy, a measure of energy, gets used up in the circuit, but current, right, the charge carriers, the amount of flow, does not get used up.